Let's get started. But before that, I want to really thank Ray and Robbie and myself, but mainly 99% Ray for organizing this wonderful workshop. So on fracture of soft materials with experts from physics, mechanics, biomedical, different areas. So we look forward this next 4 days of discussions with colleagues and students. So let's thank Ray mainly. Thank everyone. And we'll make an introduction very short. Our first talk will be given by Professor Creton, all the way travel from France. He will talk about the initiation of fracture in tough elastomers. Go ahead.
Thank you very much, Jean-He, and thank you, Ray, for organizing this really nice symposium with many interesting topics and people. So I'm really glad I could make it here. So today I'm going to talk about a relatively recent work made by essentially my PhD student, Zhan Zhu, who's now back in China. You can hear, and he worked on combining different techniques to look at cracks, really at crack tips. And there is an important modeling part here. I mean, it took a while to really try to make sense of the results and see what we could do with it. And Herbert played an important role in helping us to rationalize the data. And so I'm going to try to present his model in a few slides, and at least what I understand well of it. And I think his student is somewhere here, but I have never, Bangwo, I haven't met him. Hello. So if I say something stupid, he can correct. So the idea is to really present that, and I think he's ready now for feedback. So as you know, I'm very interested in multi-scale studying of fracture. So from the mechanics part to, let's say, the microscopic part where you have indeed this idea of damage or dissipation, or generally what happens that is non-elastic, close to cracks. And then I like to really make the link with molecules, because deep at heart, I'm a material scientist, so I'd like to give feedback to people who actually make materials so that they can understand better how to control how these materials break. So in this particular case, I'm going to combine these three length scales, so you'll see a bit of propagating cracks. You're going to see digital image correlation used at crack tips combined with mechanophore mapping of molecular damage, so which is the recent tool that I've brought to this type of study, and seeing how we can learn things from combining these two techniques and how maybe we can model them. So the materials that I'm going to use really with the same chemistry, we have two kinds of materials. So there are multiple networks. So the one that I've studied before from acrylates, but essentially what I call here single network is a standard network. I mean, it's something that anybody could make with any chemistry, just a cross-linked elastomer. So it's a large strain type of elastomer, and it's labeled with these mechanophore cross-linker that become fluorescent as they break. So this is the actual molecule. We do it ourselves, we synthesize it, and it is incorporated as a cross-linker. So which means it gets a bit overloaded relative to the main chain. Then as you take this type of network, you swell it with monomer, you cross-link it, you can make this multiple network that have different population of chain with different initial reference configuration. So some chains are stretched, some chains are not. And the highly stretched one, which is the sacrificial network, or the first network in Jumping Gong's terms, is going to be preferentially breaking. So I'm really going to compare this with this and see how these two type of network architecture lead to very different fracture mechanisms. And this is really the topic. So these are actual samples. So we made 3 different samples. I'm really mostly, so here I'm using the terminology single, double, triple like beer, but actually it's different pre-stretch. So the single network is the one that is not pre-stretched. This is partially swollen. This is the linear stretching. So in volume, it's the cube of this. And you see that also samples have different thicknesses. I don't think it matters that much for this. different young moduli, so they get stiffer, and they're also different toughness. So these are tests on notch sample, stress strain, and the SN here is in black, and you can see that when it's moderately stretched, you get some increased extensibility. And when you go to the triple network here, which is highly pre-stretched, it becomes significantly tougher. These results are not new. We've been working on this and obtained this result 10 years ago. What I'm going to show you, though, is two different ways of doing the experiment. Very slow experiment. So we're going to do, instead of just pulling and breaking, we're going to do really slow, 10 to the -4 strain rate, to actually be able to look at what happens as we do this very slow experiment. And we're going to do step loading experiment. So with the same material, we're loading, and then we wait for up to an hour and see what happens, again, in terms of strain distribution, damage distribution. Is there any time dependence there? So the talk will be really in two parts. The first part will be focusing on the slow loading. So experimentally, how do we do this? So Janzu is a really talented experimentalist. So he used a tensile tester built in the lab. And there were two types of measurement, a measurement with confocal microscopy from the top of the sample. And you can look actually all the way through the sample. And from the bottom, you can use a separate camera and a mirror to actually look. We did both dynamics measurement for DWS, but also digital image correlation to get strain field with a very classic marking of the sample. So the bottom part of the sample is marked like this. The top is not, but the top can be the activation here. If you look at these sample of cracks, this lighter color corresponds to fluorescence. It's just recolored for visibility. So we have these, the sample is the same, but the two measurements are done on two sides of the same sample. So there will be definitely some average. So the first thing I'd like to point out is very macroscopic. This is an experiment where we look at very slow loading and what happens before full fracture of the sample. So if we take an ordinary network, you can see that actually the crack slowly moves until you break the sample. This happens at pretty low extension, but I would call this continuous propagation. So you pull and the crack is moving. If you change the strain rate and you actually pull more slowly, it will propagate more slowly. This is, I would say, a classic behavior that is controlled by viscoelastic dissipation. Now, if you move to the moderately pre-stretched, you get deviation, which we don't fully understand. So I will not really talk too much about this case, but you can also see that the propagation is a bit faster. I mean, it starts well before the sample breaks, but it's over seconds. Now, if you go to the highly pre-stretched material, which is the toughest by far, now the crack doesn't propagate up to about 120 milliseconds before full fracture, and it takes about 100 milliseconds to break the sample. So even though, if you look at the stress strain curve, this is not visible, but the fracture is quite different. And if you look at the damage, so using the mechanophore, I first show here a tensile test. So what you're seeing here is a sample that is being stretched horizontally. I'm going to show you a little video, and you'll see that it becomes more blue as the mechanophore. Aha. As usual. Why is this not working? Yes. You can see here that it's stretched. This is because of cutting. And then progressively, as you stretch, it becomes blue in the middle. This is really what happens here. If you look at the stress strain in black, activation in red, you start activating molecule. Why do you start activating molecule? Because the network is very random. So you're first activating the pre-oriented molecule, the pre-stretched, even they have different length and different initial conditions. So just to say that activation of fluorescence corresponds to break-in bonds, stretch chain distribution. Now, the damage of these three different notches is something we reported before, although post-mortem. You can see that this blue one here, which is tougher, has a very large damage zone. This is something we already saw 10 years ago in the science paper where we were looking at fast propagation. So during fast propagation, you have this damage. But here, what I'm showing you is before you have any fast propagation, you already have this very big difference in damage. In the regular network, you have a very small damage zone here, which propagates continuously. In these large, highly pre-stretched network, you see a progressive damage without propagation. And then it looks like at a critical value of damage, you have a fast propagation. So which is a bit different than having a continuous and dissipation controlled propagation. What's interesting is now let's look at the strain mapping. So here it's really the same as the strain, but here we're mapping the strain rate to reduce the noise. And what we see is that at a much larger scale, so here, this is the whole sample. Before you were really looking at the tip. So you were looking at this small part here of this image. Now you're looking at the whole sample because we don't have the same spatial resolution. And you can see that the strain here, actually, and here in this case is how it moves again, but it's exactly the same as the strain in this case, is much more, you see the singularity further in the sample for the regular network. When you go to these tough network, it's very homogeneous at this length scale. So we're looking at millimeter far from the crack. It's very homogeneous strain. So it's quite different behavior in terms of singularity. So there's really, and this is the sort of thing that got Herbert interested. He said, well, there is clearly a coupling between the damage and the strain field. So can we also look at that and do something? Let me give you some additional quantitative information on this. So in this case, what we're looking at is really the strain, the epsilon XX, if X is the tensile direction, in front of the crack for the three different materials at a fixed lambda, fixed macroscopic stretch. So if I look at a small stretch, this 1.1 here, which is small because actually the regular black network breaks at around that level, but you can see that the strain is higher close to the tip for these black network here. And this is better seen in this picture. This shows the value of the tensile strain as a function of lambda at a fixed distance in front of the crack. So you're picking a point 0.3 millimeter in front of the cracks where we can have the resolution, and you're looking at the three different materials. Now, if you look at the highly pre-stretched tough material, the deformation is always smaller and only picks up when it breaks. So it stays much more homogeneous. So you're somehow having this damage suppress the singularity at a certain distance from the crack. And that was really, I think, the result that for us was interesting and maybe a bit puzzling. What can we do with this? So Herbert said, okay, maybe we could try a model with this. And one thing I'd like to keep in mind is that the damage in these networks occurs really in two steps. You first have some homogeneous damage. This actually shows how the modulus changes as function of applied stretch when you do cycles. So this is one type of multiple network, very highly pre-stretched. And this resembles very much the picture, if you've seen the one from gels, from Jumping Gong's group, they look much more like this. They have this necking procedure. But what I want to point out here is this is the first step where it's homogeneous damage. And then these sacrificial network breaks extensively. We don't really know exactly how it breaks, but it breaks extensively and the material can stretch much more. So these two steps are important. This is specific to this system. You were to use a different tough system, you would get a different damage mechanism. But the idea there is the damage occurs over a large volume around the crack. So now I have my 2 or 3 slides on the model of Herbert. So this is really the work of Herbert, Hoy, and Bango. So what they imagine is the following type of model, saying, okay, let's first of all get rid of mode 1 because that really adds complication in opening of the crack. So let's look at a mode 3 crack so that we don't have that. And let's imagine that we have a region of damage here, close to the crack tip, and we define a damage through the modulus, and we look at how this modulus changes indeed with distance from the crack tip all the way to the homogeneous material where you have the elastic solution. And how does this damage zone represented by a decrease in modulus, which then we're going to look at with a decrease with our damage measurement, how does that affect the fields? So he has inside the damage zone, he defines this G of R as a functional position as a G0 times R over rho. Rho is the total length of the damage zone at a power n. And these two different values of n corresponds of pretty much to our two networks. The n much larger than 1 here is the case of the regular network, where the damage comes very fast and goes to 0 over a very small region. This is normalized, but rho is also very small for the single network. Now, for the double network, it's much more, for the MNE, the damage is much more progressive. You first have small damage before it becomes catastrophic. So what's the consequence of having these two types of damage profile? And I think in the n much larger than 1, it's a classic case. You could separate the scales. But n smaller than 1, this progressive damage can occur over a pretty large zone, which definitely affects the stress and strain field. Looking at this in a general way, what we can say. So first of all, we can look not at the G over G0 directly, because we can't measure the modulus directly, but we can measure the damage directly. We can measure fluorescence, which has some direct connection with the modulus. So if you look at experiments, so this is the normalized fluorescence up to 1 as a function of position for our tree network. So the black here is the regular network. And you can see that if we fit the data, this is a log-log scale, we get a power 4. And if we go to the highly pre-stretched network, we get a power 0.5. So indeed, the extent of the damage and the dependence of the damage on distance is quite different for these two kind of network, consistent with what the model predicts. So you have indeed, again, black is the regular network. This is just a normalized measure of the fluorescence. So fluorescence means broken bonds. Now, the assumptions we're making here, and that's important, is broken bonds equal modulus. That's not, it's two definitions of damage. For the chemist, damage is this. You break bonds. For the mechanician, damage would be more, I decrease the modulus. For these two types of network, the relationship between modulus and broken bond is a bit different. But for the sake of the model, we have to do something. So we're going to assume that these two things are equivalent. So the next thing is we need a fracture criteria. And this is the part that for me is a bit more tricky, but I understand the logic of what Herbert wants to do. So he says, okay, the material breaks not when you have a critical elastic energy. So there's no energy release rate in this because of this mix of scales. But there is the idea that, let's say, a distance at the crack tip of the order of the feature size, so in his mind is more like the network size, then you reach a critical value of modulus GF, where the sample is going to break and the crack propagates. So this GF here depends indeed on this power n. So there is a dependence here, and the size of the damage zone also depends on this power n, as defined like that. So again, if we take our two material, the regular network has also this G equal GF. So G here is the modulus. Sorry for those who get confused. It's not the energy release rate. So the modulus get to the critical value pretty close to the tip, and there is not much of a damage zone. If you have a highly pre-stretched network, you still get close to the tip here. You will get to 0 modulus because these materials eventually break, but you have a large damage here. And so the question is, if we have a given value of modulus at the crack tip, what's the implication on the rest of the damage and the strain field? So there are a few things that are interesting. First of all, the strain field itself. So with this assumption, Herbert is able to calculate the stress and strain field as a function of distance. Now, I'm not going to go through all these calculations clearly, but if you look at this gamma here, the deformation at theta equals 0, it depends on this value here, this parameter eta, which depends on n. And this parameter eta goes from 0.5 to 0 as a function of n. So for two different values of n, this will be quite different. This actually means that this power here is -1. So the singularity is always stronger than the elastic solution, regardless of the damage model, but it's very much more singular if you have a regular network, it's -1. On the other hand, close to the tip, but of course, very close to the tip. If you have a large damage zone, it's about minus 0.6, minus 0.7. So this is really the first result. The second result is the critical value of deformation, macroscopic deformation, when it breaks for different values of n. And then you have really two cases. In the regular network, it's very close to the macroscopic damage value is pretty close to the local damage value. But for the damaging network, it's much larger. This comes from again, from the prediction of the model. So this deformation comes much larger than that. I mean, the details are all in the paper, which we just submitted. So if any of you are reviewing, be nice to us. We just send it, a little bit of advertising. And so this is really but the three conclusions we get from the model, which are qualitative, is larger damage zone in the MNE, strain field more singular in the regular network, and the fracture strain is higher. So it's still three important experimental results that can be predicted with that model. And I think this is why I spend the time really trying to explain it to you in this talk. I'd like to finish by a few results on how many minutes do I have, Shanhe? Okay, so there's a few slides, but it's not that long. So I want to talk a little bit about time-dependent behavior. So if we do step loading, it's interesting to see what happens when you wait. So you fix grip condition, you load, and you wait. In principle, if everything is really elastic, nothing should happen. But this damaging process has some time dependence to it. And if you do this experiment, you see that the stress decreases, and this stress is really related to the presence of the notch. So this is actually our different value of epsilon and our different values of the notch. So for each value, we capture the damage, we capture the strain evolution, and we capture the macroscopy value here. So the stress definitely decreases. If you go to a higher value of deformation, decreases more. If you look now at a notched versus unnotched, just to convince you, if you have unnotched sample, there is no relaxation. So these two curves here are for unnotched sample that you stretch and you wait. So if it's unnotched, so it's really the damaging area that has a time dependence and that you see over here. So it's really related, this decrease in macroscopic stress is related to the presence of the notch. Now, if we look at the strain, this is also interesting. This is the strain rate, but again, it's related to the equilibration of the strain. So close to the crack tip, you have a further extension. So you're actually increasing the extension of the sample. Further away, you're relaxing, you're decreasing, and you tend to a homogenization of the strain. So the strain actually becomes more and more homogeneous due to the damage. So the damage in this multiple network tends to homogenize the strain and reduce the stress at the crack tip. And what I would like to say is that Jianzhu tried many, many times to get propagation in fixed grip condition. He never could. So he tried to go a little bit higher, and then at some point, at the next step, the sample breaks very quickly. But he could never, of course, he's a very dynamic student. Waiting for more than an hour for him would not be acceptable. But he could not really get conditions where within an hour he could break slowly, and certainly not propagate. If you look at damage accumulation, damage accumulates also during this time. So if you look at the waiting time, you fix grip, but you increase the damage. So you definitely keep breaking bonds in this damage region. And if you go to a higher stretch, you break more bonds. You break bonds when you load. So if you load by a step, during the step, you break bonds, no doubt. This is the red line here. But during the waiting time, you also break bonds. So it's not really, it's a combination of creep and relaxation that you're actually seeing, which I think is quite typical of what happens in cracks. If we look at where you break bonds, and this is one of the reasons we waited a long time to really write this up. So this is the intensity as a function of position and integrated, so as a function of position in this direction, so in the propagation direction, but integrated over a width of 0.5 millimeters, so to get signal. And you can see that everywhere you actually have an increase. So it's not, you would expect if all the chains were the same length, it would break here much more than here. Not the case. And this is really the distribution of chain length that gives us that. So finishing with this, in increasing strain, accumulating damage, decreasing stress. So it's really a mix of creep and relaxation that we're seeing here in this system. And I think really we have the evidence. So a few, take-home messages, and I think some idea of why it's important. I think the one thing that I really believe in this is we're looking at nucleation of cracks. So in these materials, when the crack goes, actually the damage is irrelevant. It doesn't slow down propagation. This is something that was seen also by Jay Feinberg on jumping gum gels. It's all about initiation. You're delaying initiation. Once it starts to go, it will break the sample. And it's really speed of sound type of thing and just viscoelastic dissipation. Then I think that it's interesting. Herbert convinced me that the details of the coupling between damage and stress are interesting, and it's really something to explore more. And this proposal of critical level of decrease in modulus, it's an idea. There may be others. I mean, I think this is really something also for the mechanics community to see whether it's interesting or not. And as last, maybe less important comment, that the slow reorganization of the network, I think, is really due to the soft network dynamics, which is much slower. It reorganizes, causing more breakage of bond. So with this, thank you very much to the people who presented the work. Jianzhu, he now works for an appliance company in China, and Matteo, Tetsu, Gabriel, and mostly Herbert and Banguo really worked on the model. Thank you very much.
Questions? Michael first, and then.
Yes, great. I would like to relate it back to molecular ideas. So you have these two important parameters, the damage zone size and this exponent N that you were talking about, that's very important. Do you have any experimental implication of what do you change? I mean, presumably it's something in the asymmetry of the two networks. How do you control these parameters continuously, or is there a phase transition? Is it critical? If you change the ratio of the two molecular weights of first and second network or volume fractions, how do you change this zone size and the exponent?
It would be very interesting to explore because indeed, as you know, I'm very interested in molecules as well. And I would like to see how you can change this.
Any results from experiments? Have you tried changing it?
I think I mean, these are experiments that take time. You need to remake all the samples, and so we don't have any results along those lines. I think even enough to give an intuitive answer, but I think it's definitely something to do.
In an early slide, you showed images of the highly overstressed cracks propagating, and I noticed a wedge-like tip, which I associate with potential super shear or super wave speed motion. Did you check that?
So the speed is not, is definitely not above the speed of sound. I mean, we're still remaining fast, but not abnormally fast. But I think, I'm very interested, I've seen papers about the shape of the crack and some discussing it's a nonlinear behavior of the material, some saying, well, I think Oscar could be, where is Oscar? Somewhere. I mean, he had some ideas about why should it be pointy or not. So we did not look at, I mean, certainly the crack wasn't super fast.
Go ahead.
Hi, Costantino. Thanks for a nice talk. So I'm wondering if you've looked into a more detailed relationship between damage and the loss of modulus, because you mentioned that they're correlated and you're using that correlation in the model, but have you seen any experimental data?
Yeah, I think this was a long discussion because indeed we have data on the correlation between loss of modulus and the damage in the molecular damage in the chemist sense. And it really depends on the architecture. I mean, this is, related to Michael's question. There is a clear connection between the two, but it's not a simple connection. So I think in regular network, the theory would say it's a direct connection. But as soon as you have this type of more complex network, you lose it. So you really, it becomes a real problem in itself. But we have some experimental data.
Thank you.
All right, I think, get ready for the next one.
And.
All right.
Microphone.
You've been by the time.